computer audio. All right. Don't adjust your monitors. I don't have a beard. All right. Woohoo. Well, that was very annoying. But as I was saying to everybody in the classroom, and shrink everything, shrink all of it, please. Go away. Thank you. As I was telling folks on Zoom, as I was telling everybody in the classroom, for some reason, the Zoom application disappeared from my laptop. And for the past, how many minutes? 5-10 minutes? I've been in a panic trying to get Zoom to work on here, and it's working. So we're going to begin here in just a second. 05, what is today? It's Monday, November the 1st. That's right. It's the 1st of November. And of course, this is at UT Tyler. I'm not sure why I type all this stuff. I mean, all of you know this already, but in the event that somebody random watches this, they kind of know what's going on here. Okay, so again, my apologies for the delay. I had no idea that Zoom was no longer on my laptop until just now, but at least it seems to be working now. Anybody in the chat, anybody on Zoom, can you just jump in the chat and let me know if you can hear me? Okay, there's a yes, so that's good enough. All right, awesome. Thanks for joining us, folks. And again, I do appreciate your patience, both everybody in class and everybody in the Zoom session. And it is recording. For those who left last week, I realized at the very end that I forgot to tell it to record. And then somebody reminded me that when I set up the Zoom sessions, I can tell it to automatically record when it starts. So it is recording right now. So that's good. Okay, so kind of a lowdown on things going on now and then on Wednesday of this week. But today, my goal is to do several things. Number one is to answer homework questions. Number two is to review for the test. Review for test 2, which is Wednesday. I know this is all kind of janky the way I'm typing it, but my OCD won't let it go. Let's see. And also to, there we go. Also, my goal today is to cover section 5.1. I don't know if we'll finish it today, but we will definitely start it, because once we get these 2 sections done in chapter 5, and it is just 2 sections, we will be in chapter 6 and things will start being more systematic, more organized, more algorithm oriented, meaning to accomplish this thing, step 1, step 2, step 3, step 4, done. And it will be all about confidence intervals and all about hypothesis test. And it will be very, very systematic. And I think very, very easy, but we'll find out when we get there. And of course, on Wednesday, you have your test 2 over chapter 3 and 4. Mostly homework questions. So we'll talk about that more in detail when we review for the test. Okay. Next, does anybody have any homework questions they'd like to ask about? Yes, ma'am. Page 454, question 454 from section 4.2, and that is there on page 307. And I think I have a version of the textbook open. Let me share the internet with everybody. Dang, I got a lot of things open. Maybe even your test if I'm not careful. I am looking for the textbook. Here it is. And we are looking around page 307. So let's see if I can find that. It's too far ahead. 4.2. Getting closer. 4.2. We are here almost. Almost. And you said number 54? Okay, I don't know if it's number 54 in the second edition, but I'm pretty sure the equivalent question is here somewhere. We'll start by looking around number 54. I think it's number 52. Yes. All right, so we're looking at what you see on the screen as number 52, but in the third edition, which is y'all's textbook, it's number 54. All right. All right, did you have a specific question about this problem? Okay, about what is it asking? Okay, I'm glad you asked about this because number one, this is a question that is on your quiz for section 4.2. And number two, this will most likely be a question on your test, something similar to this. The trick to this is to figure out what the heck are you asking me? And once you know the answer to that, it's actually pretty easy. But to get it started, let's see. First off, these are the hypotheses. This is supposed to be highlighting. It's not. Why are you not highlighting? Fine, just don't highlight. I'll just do it this way. All right. First off, there's the hypotheses. And why is this important? Well, one of the things that I mentioned in the quiz specifically is that when you have a bell curve associated with the hypothesis test, if you have a value in the null hypothesis, that's the center of your curve. Okay, so I want to make that crystal clear. And this will be a recurring theme in chapter 6. But when you have a bell curve for a hypothesis test, whatever value is in the null hypothesis is the center of your curve. And it may not be a perfect bell curve like this one is, but if you'll notice, 50 is kind of all up in the middle of this curve. All right, so that's the first thing. Secondly, we're being asked to decide which value is closer to the p-value for the observed sample mean. Translation. When you're doing a hypothesis test, you are testing things about a population. In this case, you're testing the mean. But to test it, you measure the same thing from a sample. So if I'm going to test population mean, I test it using a sample mean. In other words, a value of X bar, which is why we have these X bar values here. Now, what do they mean by p-value? Well, generically, p-value is the probability of witnessing a sample that does that. In this case, X bar is equal to 68. The probability of witnessing a sample that does that or more extreme if the null hypothesis is true. Now, what do I mean by more extreme? Well, in this bar graph, our sample means are down here, and 68 isn't explicitly listed here, but I bet you could figure out that it's halfway between 66 and 70. So 68 would be right about here. Now, when they ask you the p-value for 68, what they're asking you is what's the probability of a sample landing there or more extreme? And more extreme means further away from the middle. Also, this is a right tail test because the null hypothesis says mu is greater than 50. But in this case, more extreme means over here. Now, when they're asking the p-value is the percent of the bar graph that lives over there. So think of these bars as filling up with water or something. And you wanted to fill up all the bars that are at 68 or further. And it's not very much. The p-value would be what percent of that picture did I just shade blue? And given the choice, let me take it down a notch. Given the choice of this or this, think of them as percents. 0.01, that's 1%. 0.25, that's 25%. So what sounds more reasonable? I shaded in 1% of the bar graph, or I shaded in 25% of it? Yeah, I sure as heck didn't shade in 25% of it. I barely shaded in any of it. So the most likely of these two, the one that's the p-value would have to be this guy, the 1%. But again, half the battle is knowing the question that you're being asked. And the question that you're being asked is, in this picture where X bar is 68, what percent of the graph is at 68 or further from the center, which in this case means to the right, and it's barely 1%. I mean, given the choice between 1% and 25%, I don't think anybody would say, yeah, you shaded in 25% of the graph. I was like, I barely shaded in any of it, much less a quarter of it. And it's the same thing for all of them. For example, the next one where the p-value for X bar equals 54. Well, 54 is right here. And if we were to talk about the p-value for 54, what we're being asked is what percent of this bar graph is at 54 or more extreme? Well, the center's at 50, and this we have to know where the center is. So if I were to shade in all the bars from 54 onward, more from the center than that, and then ask you which of these two numbers is more likely what I shaded in as a percent of the graph, well, what would you say? Would you say that where the green is, would you say that's probably 10% or 30% of the graph that I shaded in? I'd say 30%. It's almost half of it, and 30 is closer to 50% than 10. So the question is, what percent is here or more extreme? And you could probably answer the third one without me drawing anything. Locate 63 on the number line on the bottom. It's somewhere between 62 and 66, but it's to the right of center. So what percent would you say is at 63 or further to the right? Would you say it's closer to 5% or 50%? 5%, because 63 would be about here. And then there's that part of it. So in terms of the whole picture, I would say that the part in that right tail is more likely to be 5% of the graph than 50%. And that's all it's asking. Okay. And, you know, this is a tricky something to wrap your mind around, but once you wrap your mind around what a p-value means, a probability, or in this case, a percent of a graph, then it's a little bit easier to approximate, especially when you're given two numbers and asked to choose one. Okay, and just for the record, number 54, all three parts of it are on the quiz. So there you go. You're welcome. Thank you for asking about that one. Does anybody have any other questions on number 54? Okay, any other questions? We're going to go bang, bang, bang. Yes, sir. 72. Let's see, that's multitasking in the classroom. I'm not sure if that equivalent question is up here. We'll see. If so, it'd probably be number 70. And I don't see it. Let's see. It looks like they changed all the word problems. If you break an arm, use your brain. I'm looking for one about multitasking in the classroom. I'm not seeing one. Let me scroll the other way. Let's see. Colonoscopy, anyone? Red or pink display of fertility. Football experience and brain size. Do you own a tablet? Concussion and brain size. I'm not seeing it on the PDF. That's okay. What I'll do is I will switch over to the whiteboard and just manually do the problem as much as I can. There's something I like to do real quick. Close a bunch of this garbage that's open on my computer. I don't need this. Oh, that picture was copy and pasted into your test. So not that it really gives you an advantage or anything. And for those in Zoom, they're like, wait, I can't see all the things you're opening and closing. Don't worry. It's nothing of consequence, but I think I've opened just about everything. Yes. Okay. All right. So let's take a look at number 72, multitasking in the classroom. I'm not going to write everything from question 4.72 on page 309, but I will carry over the important stuff as necessary. All right, so the question is talking about whether or not multitasking basically affects grades. A lot of times you can skip a lot of stuff at the beginning and go closer to the end. I'm going all the way down to the sentence before the hypotheses that starts with using, and it says using mu1 for mean grade on material when devices are not allowed, and mu2 for mean grade on material when devices are allowed. And when they say devices, they mean things like electronic devices. Then they have some hypotheses. So up here, I'm going to define them. Mu1 is mean grade when devices aren't allowed. And mu2, and this comes right from the problem. Mu2 is mean grade when devices are allowed. And our null hypothesis is mu1 is equal to mu2, because the null hypothesis always says, yeah, they're equal. And the alternative says, well, we think mu1 is greater than mu2 because when devices are allowed, then your grade drops. Now, we're also told that we have two samples. Two samples, or really I should say two pairs of samples. Yield the following. And as badly as I type mu, in order to type x bar, I just type x bar. X bar 1 minus x bar 2 is equal to 2.8. and x bar 1 minus x bar 2 is equal to 5.7. All right, so there's the setup. Now, was there a particular part of this problem that you wanted to ask about? The whole thing. Okay. This is another example of what is it you're asking me, because the minute you know what they're asking you, the better off you are. Do you remember a minute ago when I said, and this should be an equal sign down here. Do you remember a minute ago when I said that when you're drawing a bell curve for a hypothesis test, the number in the null hypothesis is the middle of the bell curve? There is no number in this null hypothesis. There is no number right here. Or is there? Now, in the quiz, I gave a hint on a problem involving a hypothesis test with a variable on both sides and asking where the middle of the bell curve is. Where's the number in this null hypothesis? Well, you don't see it unless you write it differently. If I were to subtract mu2 from both sides, I could rewrite my null hypothesis like this. Hypothesizing that mu1 is equal to mu2 is the same as hypothesizing that their difference is 0. So there is a number in the null hypothesis, you just don't see it until you move all the variables to one side. And since that's the hypothesized value of the difference in the means, that would be the middle of our bell curve. And what the null hypothesis is saying is, all right, we think that these means are equal for these two populations. So when you go measuring samples and subtract their means, it may not be exactly 0, but it might be somewhere near 0. It might be, and I'm going to use some stamps because it's kind of fun. It might be here, or maybe when you subtract them, it might be here. But your samples, when you take two samples, one from each population, and subtract their means, it's probably going to be somewhere in the middle. It's okay if it sways left or right a little bit from the middle, but it shouldn't sway too far. Because if we have something that lands over there, that's a little bit too far, and we're not supposed to see something way over there if the center of our bell curve is correct. Participants can now see your whiteboard. Could they not see the whiteboard before? Okay, well, my apologies to the Zoom crowd if you're just now seeing the whiteboard. I thought I had shared it before. In fact, you have to be seeing it because I can't see it myself unless I share it. But I just didn't notice that I totally misspelled grade. Well, not totally. Okay, they could see it. All right, thank you, everybody. Okay, so anyway, when you're hypothesizing something about a variable, you're basically saying this is the middle of our bell curve. And in this case, we're hypothesizing that one variable is equal to another. In other words, one population's mean is equal to another, which is the same as saying that their difference is 0. So anytime you have a hypothesis test that is comparing one population to another, mu1 equals mu2, p1 equals p2, sigma 1 equals sigma 2, we won't see that. But anytime you have a null hypothesis comparing two population values saying that they're equal, the center of that bell curve will always be 0 because you can always rewrite that as saying that their difference is 0. Now to the questions. All right, we're told that we found two pairs of samples and one of them gave us a difference of sample means of 2.8. Let's say 2.8 is right about here. I would need more information to know exactly how far from the middle, but I just know it's to the right. But we took another pair of samples and the difference in their means was 5.7. So just because I want to put some things here, there's one of them and there's another. All right, so before we look at the questions, does anybody have any questions about why I put 0 in the middle? One more time as a generic blanket statement. When you have a bell curve for a hypothesis test, the center of it is always what the null hypothesis, the value in the null hypothesis. The stealthy version is when your null hypothesis doesn't have a value, but rather has one parameter equal another, in this case, mu1 equals mu2. But if you subtract to create a subtraction problem equal to 0, that's the value in the null hypothesis. We're hypothesizing that the difference in these population means is 0. Now for the questions. Part A says which sample result, A, and I didn't label these A and B. A and B. That's a colon after the B, maybe. Which sample results will be closer to the center? Well, at this point, I think it's a trivial question. Here's sample A's results. Here's sample B's results. Which one's closer to the center? A. A is closer to the center. Second part, which sample result will be farther out in the tail? Well, that would be B. It's further out. Now, when they say of the randomization distribution, what they're saying is if we randomly generated samples according to this null hypothesis, we'd make a bunch of dots in a dot plot that would be kind of bell curvy. But starting today, we're going to transition from things that kind of look like bell curves, like the dot plots and the bar graphs, to just flat out drawing bell curves. So, but yeah, the one that's further out is the one further from the center, which is sample B. And so C, which says which sample result, A or B, will provide the stronger evidence against the null and in support of the alternative. Well, the null basically says that the center of our picture is correct. And which one of those says, I'm not so sure about that? And the answer is the one that's further away. Why? Think of it in terms of p-values. We don't have p-values, but if I were to figure out a p-value for the 2.8, it would be the area over here, what percent of that area that is. But if we were to think of the p-value for the other sample, it would be the area of this tail over here. Well, which would be a smaller area, the pink tail or the green tail? The green tail would be smaller. And if you remember that p-value is that area, it's also the probability of seeing what you saw if the null hypothesis was correct. So there's a lot less likely chance of seeing a value of 5.7 than there is for 2.8, just based on the picture alone. So which one provides stronger evidence against the null? The one further from the center. The one further from the center will always provide the stronger evidence against the null, because the null says our center is here. Samples, you're allowed to deviate left and right a little bit. Just don't go too far. And you got that one that says, look at me way over here. You're not supposed to be over there. The middle's here. You can't be at 5.8. Well, maybe the middle's in the wrong place, AKA maybe the null hypothesis is wrong. So in short, the first three answers are A, B, and B. And for part D, explain in the context of the situation what it means to, quote, provide evidence against the null hypothesis and in support of the alternative hypothesis. Well, that goes back to interpreting what the hypotheses mean. Since the Muse are measuring mean grades, whether or not devices are allowed, the null hypothesis says it doesn't matter whether or not you use devices, your mean grades are going to be the same. And the alternative says no. If you don't use devices, we think your average grade is going to be higher than when you do. So if we reject the null because we got a sample that's too far from the middle and accept the alternative, what we're saying is evidence supports that the mean grade is higher when devices aren't allowed than when devices are allowed. And that's how you would interpret it in the context of the problem. But again, I think with the picture and knowing what the questions are asking, this is actually a really easy question. If you know that it's a bell curve with a middle of 0, and the further from the center you are, the stronger evidence you provide that your null hypothesis is wrong, or that it should be rejected, I should say. All right. Does anybody have any questions about number 72, which is also in your quiz, and I just answered all of it for you? Actually, I didn't ask you part D, because that would either require a lot of multiple choice options or you typing in an answer and me having to go in and grade it. So I just asked you A, B, and C. All right. I know there were some more requests. We were bang, bang, bang. Yes, ma'am. 56. You guys are asking questions like you have a test Wednesday. It's because you have a test Wednesday. All right, 56 should be 54 on here. So let's go back and see if it's the same problem. 56, 54, 54. 56 is the D equals, 54 is This is structured a little bit differently. Oh, wait, is this it? Okay, oh, there's 54. I kept saying 54, 54, and I kept skipping over it. All right, so we're going to take a look at this one, which is number 56 in your edition of the book. Now, was there a particular part of the question you wanted to ask about, or just go through the whole thing? Okay, now, having had the discussion that we just had about a bell curve with the hypothesis test and where the center is located, and stronger evidence means further away from the center, and p-value is area of the tails, or the area of the tails. This might be a little bit easier to get through. First off, notice that our hypotheses are comparing two population means. We don't even have context here. But just the fact that we're comparing two population means that the center of this curve should be 0, because we could write that as mu1 minus mu2 equals 0. And so we're hypothesizing that's the middle of our curve. And if you scroll down here and look at this bar graph, 0 is pretty much in the middle of it. So that's consistent. And now we're measuring the same value. Well, I say we're measuring the same value because the hypothesis isn't saying anything about mu1 minus mu2. But as a single value, we would measure the means from two samples and subtract them. And if our null hypothesis is correct, it should be fairly close to 0. Well, in part A, the difference in the sample means that we calculated was negative 2.9, and we want to know what the p-value is, which means we're looking for the area of a tail that's cut off by this sample means difference or more extreme. Negative 2.9 would be right about here. So if I wanted to be there or more extreme, in this case, we're to the left of center, so we're saying more extreme, so more to the left, it would be the area of those bars. But this is where it's a little bit tricky, and something that I'm going to go into more detail as we move forward. It's not just the left tail. How can you tell in this problem that I don't need to look at just the left tail? Hint, one of the hypotheses determines what type of test it is. Two-tail test. The alternative hypothesis will dictate left tail, right tail, or two tails, and not equal to is always a two-tail test. Now, what does that mean here? Look at both sides. It means when we say the p-value of negative 2.9, that means the probability of hitting negative 2.9 or more extreme on both sides. Well, if 0 is in the middle and we go 2.9 to the left, then we also have to look at 2.9 to the right, which would be positive 2.9. Not sure why I put 2 decimals in that. So when you're doing the p-value for a two-tail test, it's not just the area in one tail, it's the area in both tails that are the same distance from the center. But either way, as a p-value question, it's asking what's the probability of landing in both of those tails, which is the same as asking about what % of that bar graph did I just shade. And if my options are 1% and 25%, I think I know which one I'm going with. Which one? Yeah, I hardly shaded anything. So if you tell me, if you say, did you shade 1% or 25%, pick one, then I literally have to pick 1%. So the p-value on A is 0.01. And for B, it's the same thing. I'm going to clear the screen here. For B, it's the same thing. We just have a different value. The value that we're looking at is 1.2, which is, I missed a mark there. 1.2 is about here, which means we would need to know the area at 1.2 or more extreme, which would be to the right. So the area of all these bars, but it's a two-tail test. So I would also have to go back to negative 1.2 and consider being there or more extreme. Well, to the left would be over there. So if I were looking at 1.2 in a two-tail test, the p-value would be what % of the area is shaded in if I shade in those two tails. And if my choices are 30% or 60%, well, what do you think is more reasonable? Did I shade in yellow about 30% of the bar graph or about 60% of it? I would go with 30. And my argument would be there is more unshaded than shaded. I know I shaded in a lot of bars, but they weren't that tall, and some of them were very small. The unshaded ones are much taller by contrast. So if you think about it as the percent of the area that's shaded, and given the choice between 30% and 60%, I would go with 30%. And that would be the p-value in part B. But that's all p-value is. It's the area of the tail or tails cut off by the test statistic. And if it's a two-tailed test, then you have to cut off the tails on both sides. And the p-value is the area of those tails. I'm going to go back to the whiteboard and type what I just said about p-values and areas of tails, because that is going to be super important for what we do in the next section. All right. So visually, the p-value for a test statistic is, let me widen this text box and I'm going to make the font size a little bit larger. The p-value for a test statistic is the area of the tail cut off by the test statistic. If it is a two-tail test, then the p-value is the area of both the left and right tails. Let me put total in front of area. Is the total area of both the left and the right tails, as was evident in that previous example. Oh, there is one more thing that last Wednesday I realized I could do in my Stats 2 class. I'm kicking myself for not remembering this earlier. Everything that I type and draw in the whiteboard, I can save as a PDF and upload to Canvas. Because for some people, they just need the visual and they don't need to watch the whole video to see everything. So I'll try to remember, because I have to do it before I stop the record, before I end the Zoom session. But I'll try to remember to save everything written in the whiteboard as a PDF. Now, of course, you'll see it all at the end. You won't see it, you know, written in real time. So you'll kind of have to remember what happened. But I think that would be helpful. So I will try to save these Zoom whiteboards as PDFs in addition to saving the recording. So that way it's almost like a transcript of what you saw. Okay. But did that kind of help with number 56? Yeah, you know, the more we talk about this and the more we do, the more it starts coming together. But even if it doesn't come together perfectly for test 2, we will continue to talk about it for the rest of the semester. And by the time we're done, hopefully it'll be a lot more intuitive. But it is a tricky thing to figure out at the beginning. And I think we had one more question. Yeah, and again, I take the blame for not clarifying that previously. But if we look at number 50, which I believe is number 48 in this version, here's the question right here. But the instructions, which of course are on the previous page, were to, let's see, where's the center? And is it left, right, or two-tail test? As we actually get into the process of doing hypothesis test systematically, step 1, step 2, step 3, step 4, the bell curve in its center will become second nature. But yes, when your null hypothesis is saying that one parameter is equal to another, you can rewrite it as their difference is equal to 0, which means the center of that bell curve will always be at 0. Now, in one like number 46, it's even easier. Here's the center, 10. Here's the center, 0. Well, that's the only two that are above it. Yeah, but if it's just one number, then that's the center. But if it's one letter equal to another, then the center is always 0. Well, we'll just say yes, but in the back of my mind, I know that there are situations where it's not, but we won't ever encounter those, not even in Stats 2. Okay. All right. It is 4:52 and we've got about half an hour left. So I think we should spend some time talking about what you need to be able to do on your test. That makes sense. And all I'm going to do is go through the homework problems, which I believe I have somewhere around here. Don't need that. Let's see. Let's go into the modules and look at the homework assignments. This does not look right because this is stats 2. You'll notice in my stats 2 class, we just went back and reviewed some of chapter 2. But it would help if I actually went to your class's Canvas shell. And let me make sure that everybody in Zoom can see where we are. They can. All right, homework assignments for you guys are right here. I have started writing your test. I haven't finished writing it. I am currently in 3.2. I'm not going to tell you which homework questions I picked, but I pretty much just am going through the homework and saying, I like that, I like that, I like that. I don't think I've changed any numbers either. If you've done your homework, done the quizzes, there are no surprises on this test. Well, I take that back. There is one other thing I kept saying, I'm going to test you on the second test. I'm going to test you. I'm going to test you because you got to know it. You got to know it. You got to know it. Does anybody remember what that was? Matching variables to variable names. Matching variables to variable names. So why don't we start there? Okay. Test 2 review. Number 1, know your variables. I'm not going to write every variable and their name. I will write the variables and we'll say what their names are. And if you want to write it all down, more power to you. What's that? It's a Greek letter mu, but what variable is it? Population mean, and its sample counterpart. X bar is sample mean. Okay, so that's 2 of them. How about this one? P. Population proportion and its counterpart, P hat sample proportion. Now the name you're going to match P hat to isn't P hat. That's how you read it. You would match it to sample proportion. What about this versus this? Population size and sample size. Here's one we haven't seen in a while. Standard deviation, population and sample. Population is if it's a Greek letter, it's from a population. Population, standard deviation, and sample standard deviation. These 2. Rho and R, correlation. Rho is population correlation. R is sample correlation. What's that, 10? And there's one more. Alpha, which is what? It has to do with hypothesis testing. Significance level. So I'll say them one more time from left to right. Population mean, sample mean. Population proportion, sample proportion. Population size, sample size. Population standard deviation, sample standard deviation. Population correlation, sample correlation, and significance level. They will not be in that order. They will not be separated by population versus sample. They're all mixed up. As random as I could randomly type things, but how random is random these days? All right, so you need to know those. All right, so what else do you need to know? Well, going back to 3.1, I can't stress enough that your best strategy is to go over the homework. Within that is your test, in addition to knowing your variables. But from 3.1, you need to know, you need to be able to identify correct variables in context. And I will switch back over to the book to show you what I mean. I'm going to the beginning of section 3.1. In my mind, I'm debating whether or not I'm even going to start chapter 5 today. I'm leaning towards no. It'll put me in a bind, but I'll worry about that later. I know some places where I can sacrifice something. Going back to 3.1, and I gotta find it real fast. So give me a second here. It's not 224. It's got, well, actually, it may be around 224. Oh, it's right there. Okay. So when I say, what was it I said? Identify correct variables in context. When I say that, I mean things like numbers 1 through 5. Is it a parameter or a statistic, and give the correct notation? Just remember that parameter simply means a variable for a population, and statistic means a variable for a sample. So in deciding that, it's kind of important. For example, number 1, average household income for all houses. I see everything I need to know. Average of all means population, average means mean. So it's population mean, and what variable is that? Yeah, for those who aren't instantly going, oh, population mean, that's mu, you're in for a world of hurt. Oh, population mean, that's mu. The minute you've determined it's population and mean, you should say mu. Or like on let's see, looking for a good one, like proportion of people who use an electric toothbrush from a sample. All right, sample proportion. What variable is that? P hat. All right. So that's what I mean by identifying the correct variable in context. And the first batch of questions from chapter 3, section 1 homework is pretty much like that. Let me look at the list of homework of problems again from 3.1, 1 through 11, and then 16 through 20. 16 through 20, what is that? Oh, this. I'll go in and type something in the whiteboard in just a second. But problems like this, where you're given some sort of distribution and you're asked something like, okay, I don't want to go over that particular question. Gee, I wonder why. I wonder how good at inferences you are. Let's take a look at this one. Number 17. Using the sampling distribution shown, how likely are the sample means? Now in this one, you were given several phrases to choose from. Reasonably likely to occur, unusual but might occur occasionally, and extremely unlikely to occur. So on one like number 17, where you're given different X-bar values in a picture, the X-bar values are 70, 100, and 140, and a dot plot like this one, distribution. Where's 70? Oh, it's all up in this, isn't it? Well, that's pretty likely to occur. Look at all those dots above there. What was the next one? 70, 100. That's also all up in there in a bunch of dots. So it's also likely to occur. But when they said 140, which is over here, well, there's a dot over there or two. So it's unlikely, but it could occur occasionally. Now, if they had said something like 170, which would be over here, that's not even in the picture. That's highly unlikely to occur. So given the option of, it's reasonably likely, it's unlikely, but possible, or extremely unlikely, it's really a question of how many dots are around that neck of the woods. So a question like that, it's really not a difficult question to answer as long as you understand the question being asked. So how am I going to phrase that? We'll say we're going to call that, let's call that, given a dot plot, describe the likeliness of a sample occurring. So we'll just say 3.1 numbers 16 through 19. And I could probably give you specific homework problems for all of these, but I'm just going through the homework, folks. That's all I'm doing. All right, let's see what else we got. The next batch of homework was, let's see, we're still in 3.1, so let me highlight that. 20, 22, 24, and 28. Let's take a look at those. And again, these numbers may not be perfectly aligned. 20 is the same as mine, 22 is the same, 24 is about topical painkillers, and 28 is about proportion of residents less than 25 years old, which is actually 26 in this book. On all of these word problems, let's just take a look at number 20 real quick. Give the parameter of interest. When you see this phrase, the most important thing to remember is that when you see the word parameter, it is referring to a population. I think I did this before. Listen closely. I'm going to exaggerate. Parameter, population. Statistic, sample. Did you catch the alliteration? Parameter, population. Statistic, sample. So when it says give notation for the parameter, they're instantly telling you we need a population variable. And when they say parameter of interest, now you got to figure out which one it is. Out of 461 smartphone users, 355 have downloaded an app. What measurement can we get from our population based on those numbers? Proportion. Remember, proportion is what percent of a population possesses a characteristic. Well, 355 out of 461 could be turned into a percent. So the parameter of interest would be P. Now, when it says give the notation for the quantity that gives the best estimate, this is where you have to remember that the phrase best estimate means measurement from a sample. And the reason it's an estimate is because populations are too large to measure accurately. And so we get a measurement from our sample to estimate the measurement for the population. So in this case, it says give the notation for the quantity and give its value. So not only does it want you to know that it's the sample version of the parameter of interest, but how to calculate its value, 355 out of 461. Of course, you could divide that and turn it to a percent if requested. And then for part C, what would we have to do to calculate the parameter exactly? Well, parameter is measuring what? I can hear some of you during the test going, and that's okay. Just don't spit on anybody. What would we have to do to calculate the parameter exactly? Well, to measure the population exactly, we would have to talk to all smartphone users in the US. Problem is that population is dynamic. Somebody who has a smartphone today may not have one tomorrow and vice versa. So we really couldn't do it. But if we had to, we would have to talk to everybody who has a smartphone. Or if we could stop time and then walk all over the country. Yes, no, look at their phones while they're frozen. But that's really unrealistic because you wouldn't have enough time. And the fact that stopping time currently is not a thing that we can do. But for all I know, it is. And none of us know because we can't see the people when they stop time. Conspiracy theory. All right, so this is just another what variable is it? And really that's what 3.1 was mostly about. What variable are you talking about? Is it from the population? Is it from the sample? Just remember, parameters from a population. So parameter of interest just means what am I measuring? But when you see the phrase best estimate, that means the value from the sample. You estimate about populations, you measure samples to get that estimate. All right, so how can I phrase all that? Oh, I don't know. I think it's pretty much says exactly what I said here. So make sure you can identify correct variables in context because really that's all that was. Okay, and I think that's pretty much it from 3.1. All right, so let's talk about 3.2. From 3.2. All right, looking at the homework from 3.2, which is, I'm going to do myself a favor. I am going to go to this and I'm just going to take a picture of this page so that I don't have to constantly go back and forth. So give me 1 second to get my camera to cooperate, take a picture of that. And now I can see all the homework assignments without having to bring this page up again. Let's just hope my phone doesn't die. Okay, so from 3.2, which was on page 242. So let's just type in 242 and see where that takes us. We are still in 3.2, and the homework begins around here. All right, so the first problem's here. Hey Siri, turn off low power mode. Got tired of my phone going to sleep. Let's see. So we started with 44 through 58 even, which in your book, well, it starts with number 44, but in this book starts with number 41. So we're going to have a little bit of discrepancy between the numbers I say and the numbers you see up here on the screen. But as far as 44 through 58 even, well, this is the song and dance that we just got finished playing. Give the notation for the quantity that is being estimated. You estimate about population, so that's population parameter. And give the notation for the quantity that gives the best estimate. That's the sample version. So this is just another example of identify the correct variable in context. Let's see, going through 58. Let's see, we'll just keep scrolling through here. Oh, construct an interval giving the range of plausible values for the given parameter using the given sample statistic and given margin of error. All right, we haven't seen this in a while, but when you're making a, let's see, an interval, your intervals are always of the form something in the middle plus or minus a margin of error. So it's actually pretty easy to do. And so let's list this under, how did I overlook this? Maybe I'm not on section 3. Maybe I'm still in 3.1 and writing the test. Dang, I get that thing written. All right, so from 3.2, you need to be able to build an interval, comma, given a center and a margin of error. And that's really easy to do because all you have to do is take the center plus or minus the margin of error. Now, it is worth pointing out that the center, is always some sample measurement. Or I guess to use the lingo, it's always some sample statistic. So for example, if you want an interval to estimate a population mean, you would center it at a sample mean. Or if you wanted an interval to estimate population proportion, you would center it at a sample proportion. All right, now specifically, when you have a 95% confidence interval, to make a 95% confidence interval, if you are given the standard error, which I had always called SE, then the margin of error equals 2 times the standard error. And somebody had asked me, and I think it was you, that said, isn't it really 1.96? That was you, wasn't it? And my answer was yes, and we're not there yet. Well, we're practically there. If we were starting chapter 5 today, we would be there. That'll have to wait till next Monday. All right, so to make a 95% confidence interval, if you're given the standard error, then the margin error is 2 times the standard error. This is borderline a formula, and so what you see here will be given to you. Maybe not in those exact words. It will probably say something like margin of error for a 95% confidence interval. Margin of error equals 2 times standard error. But any formula I give you, and that is barely a formula, but it is a formula nonetheless. All right, let's see. Okay, what next from 3.2? Then we have these run of word problems starting with 60, 62. You know, this is almost more of the same. What variable is this? What variable are we estimating about a population? What variable is the best estimate? That comes from the sample. And just one more thing about this. I'm going to slide this all up a little bit. One second. Let me capture all of this. You are captured. And everybody move up, please. Thank you. All right. So one more thing, and really that's it for 3.2. Dang it, what was I going to say? Oh yeah. Know when a value is quote unquote plausible for a parameter. And all that means is whether or not it is inside an interval. I'll show you an example real quick, but if I ask you, is it plausible for the population mean to be this? Then I'm asking you, is it inside the interval that we created? I'll switch back to the whiteboard in just a second. But an example of a question like that is, well, look at 49 and 50 here, which in your book is actually 51 and 52. Like on number 49, a 95% confidence interval for the mean is 112.1 to 128.2. Is the value given a plausible value for mu? Well, asking if this is a plausible value is just asking you, is it contained in this interval? And if it is, then the answer is yes. Otherwise, the answer is no. So in order, the answers are yes, yes, and no, because the first two numbers are inside that interval, but the third one is not. So that's all it means to be a plausible value for a population parameter if it's inside the interval that's estimating it. So it's a pretty easy question. Just remember, plausible means it's inside the interval. Okay. Yeah, that's pretty much it for 3.2. So we'll take a look at 3.3 now. And while I'm getting this set up, I cannot stress enough that your questions for the test are pretty much coming straight from the homework. Now, 3.3 is where things started getting annoying. That's when we started doing bootstrapping samples. And I think this is the one where I only gave you 2 or 3 homework questions because I said I didn't want you to have to use StatKey to answer them because then everybody gets different answers. And then in 3.4, I had actually made up my own homework assignment. So we'll say from 3.3, worry more about 3.4. And what that means in terms of me writing the test is that I probably won't pick any questions from 3.3. I'll just go on the record and saying I'm not going to pick any questions from 3.3, but I will be asking you more about things from 3.4. As a reminder of what those were, let's go back to here and let's go into Canvas for a second and see what that homework assignment was. Let me download it and open it in another tab. And so I can blow it up. Y'all remember this homework? It was the one I created. I would expect a lot like this. In fact, I would expect a problem. It's not going to be exactly this or exactly that, but it will be the same questions with the different dot plot and different numbers. So let's just go over this real quick. Well, when I ask you what, and we'll do some highlighting here. When I ask you what population parameter is being estimated, that's a population variable. Well, you can read the words, or you can look all over this picture and see the words proportion everywhere. Proportion, proportion, proportion. So this is all about proportions and population parameter. And I'll tell you right now on your test, I will not put the word population because by now you need to know that parameter comes from a population. And I will always emphasize the P in parameter and population unless everybody nails it on this next test, in which case I'll stop doing it. So if I ask you what parameter is being estimated, I won't even put that. Just look around and see what parameter they're talking about. You got to be careful because there is the word mean here, but that doesn't mean we're talking about averages. Sometimes you may have to go back and look at the context where I actually say the word proportion. What's the value, the best estimate? Well, best estimate means the sample version of what we're estimating. So that would be what is P hat equal? But this is where you have to be careful and remember what's going on here. I think what I will do, because this really confused some people when I made this homework assignment, what I will do when I create this is I will get rid of this. so that you'll know that this is from the original sample. Because remember how a bootstrap sample worked. We had a sample and then we made more samples by picking from it with replacement. It's like if I said, everybody write down on a piece of paper, I like pina coladas. Yes or no, just pick an answer. You write your answer in a bag and say, look, all right, we can figure out what % of you said yes. Now let's draw them all again, but now I can replace them. So if there were 25 of you, I would draw out 25 answers and put them back in each time I draw them, and then calculate a new p-hat and do that over and over again. That's where all these dots came from. But when I create these problems, I'm going to lose the specific bootstrap sample box, because that just says, hey, for one of these dots, and I don't remember which one it was highlighted over, but the proportion was 25%, so it had to be one of those three. For one of these dots, this is what happened, but I think that really more confuses things than not. So I'm going to take out that bottom part where it says bootstrap sample, and then be able to do the rest of these. And again, none of the answers that these require are in the thing that I crossed out. You do need to remember the following. When you have a confidence level for a confidence interval, that always refers, can I type in this? I thought I could, but I cannot. The confidence level always refers to the middle area. So when I say 90% bootstrap confidence interval, oh, it even says there, I'm gonna take that out before I write this. Recalling that this means the interval contains the middle 90% of the dots in the dot plot, I'm going to take that out. So when I say 90% confidence interval, that means 90% in the middle, which leaves how much left for the two tails together? 10%. And so half of 10% is 5% there, 5% there. But when you make this bootstrap confidence interval, and I'm going to say this, then I'm going to go back and type it. The flow is, all right, there's a big chunk in the middle. Now, what % are in the tails? 5% in each tail. There are 100 dots. So 5% of 100 is 5 dots. So you find the 5th dot from the left, 5th dot from the right, and see what numbers it's over. So yes, I'm going to ask you to do all that. Let me go back into the whiteboard and type what I just said. All right, so from section 3.4, given a bootstrap distribution dot plot and a confidence level, determine a confidence interval by doing the following. I'm going to widen this, take the font size down a notch. Actually, I think the font size is okay. All right. So given a bootstrap distribution dot plot and a confidence level, determine a confidence interval by doing the following. All right. Number 1, figure out what % is in each individual tail. And I can even elaborate on that. It's half of 100% minus the confidence level. So for example, and this is easy to do. Let's see how fast you can answer these. You should know this one. It's the one I just drew a picture of. If there's 90% in the middle, what % is in one tail? 5%, okay? Now, if there's 80% in the middle, what % is in one tail? 10, half of 20. What if there's 95% in the middle? 2.5%, 98% in the middle, 1% in the tail. Y'all understand where these are coming from? 98 from 100 is 2, half of 2 is 1. So 98% in the middle, 1% in the tail. So figure out what % is in each individual tail. And then number 2 is calculate that % of the number of samples. So for example, if there is if there's 90% in the middle, then there's 5% in a single tail. And what if we have 200 dots? Does anybody know 5% of 200? It's 10. And if you didn't know it instantly, that's okay, but you should know how to calculate 5% of 200. Turn the percent to a decimal and multiply. So that's what I mean by calculate that percent of the number of samples. And then you count off that many dots from each end. Those are the numbers for your confidence interval. And when I say those are the numbers, I mean the numbers over which the dots are living. So if I count off 10 dots from the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I see what number that 10th dot is over. And the same thing when I count off 10 dots from the right, I see what number that 10th dot is over. That is your interval. Okay. It was homework 3.4. Make sure you know it because I'm going to ask you to do it again. All right, and that takes us to chapter 4, which we did a lot of discussion on just today in answering some of the questions. So this rest of the review is going to go a little bit faster. All right, so for 4.1, let me just look at 4.1 and tell you the main ideas I'm going to ask you about without looking at the specific homework problems. In 4.1, you need to be able to write null and alternative hypotheses using the correct notation. And when I say using the correct notation, there are two key things I'm looking for. Number one, it's about populations, not samples. So if you say null hypothesis, X bar equals, I'm gonna cross it out with a big X, put a frowny face on it, and then put something constructive. But it's always about populations, not samples. And the null hypothesis always allows equality, whereas the alternative never allows equality. So when you write your hypotheses, I am looking for very specific notation. For example, if somebody says, and I'll just do a real quick example, we speculate the mean is different than 5. And I ask you, or something with a little bit more context, and I ask you, turn this into a pair of hypotheses. Well, first off, what variable should we put? Mu or X bar? Mu, it's always about a population. So mu. Now, when we say different than 5, what can we put between the mu and the 5? Not equal to. And because it's not equal to, which hypothesis is this? Null or alternative? Alternative. So that would be the null, excuse me, that would be the alternative. And in the absence of a clearly stated, oh, forget that, the null is always going to say equal. Deep in my deepest recesses of math, I know that's not always true, but for our purposes, the null will always state equality, not allow it, but flat out demand it. All right, so make sure that you can write hypotheses. Let's see. Also, this is still 4.1. Identify evidence against the null, both visually and numerically. I'm just going to say this because we're short on time. For example, if somebody wanted to challenge the claim that the proportion of something is 40%, and they think that it's more than 40%, which is the stronger evidence in support of more than 40%? A sample whose p-hat is 45 or a sample whose p-hat is 55? 55, that's more than 40% than 45% is. In other words, the further away from your claim, the stronger you are against the null. And visually, it's, the box plots being further apart or one being further to the left or right or something like that. So identify evidence against the null, both visually and numerically. Let's see, that was still under 4.1, and I probably could have fit this on the previous page. So give me 1 second. Oops, damn it, I hate it when that happens. All right. I know you feel like I might be, why are you wasting all your time doing this? Because I know this is going to turn into a PDF and I want it to be as good as I can make it, you know, all things considered. Okay. All right. 4.2. Understand what p-value means. Understand what p-values mean. And remember that a p-value is the probability that you saw your sample or something more extreme if the null hypothesis was correct. And also remember that smaller p-value equals stronger evidence against the null. If you just remember p-value is probability. Like if somebody's on trial and they say, well, we found this evidence and the probability of it happening if you were innocent is 50%. I can't convict somebody on that. Or we found this evidence, and if you were innocent, the probability we would have found this evidence is 1%. Oh, that's pretty strong. Yeah, you're probably guilty. Let's see. Oh, to measure a p-value from a dot plot, calculate the percent of dots that are as far from the center or further than the sample statistic. In other words, let me find a picture real quick. I'm going to switch to the book online. I'm going to look on page 302, but it's probably not exactly on page 302. So we will see. Book, please. We're almost there, folks. Be patient. All right. Here we go. And I'm just grabbing this dot plot because it's handy. Like if I asked you, like if there was a number here and I asked you what's the p-value, I'm asking you what percent of the dots are over here. So p-value is just percent of the area to the left or to the right of a given value. And if it's two tail, then it's both tails. Let's see. Oh, speaking of tails, at this point, I'm abandoning specific sections and just telling you things that you need to know. You need to be able to identify left tail, right tail, and two tail tests. And it's all based on the alternative. You need to be able to locate the center of a bell curve for a hypothesis test. We did that today. It's what your null hypothesis says, unless it says one letter equals another, in which case the center is always 0. You need to be able to, what else did we do earlier today when you guys asked me questions? You need to be able to pick the quote best p-value for a given picture. So like we did at the beginning when everybody was asking me about the p-values and the pictures. Let's see. Now there is one more thing that, oh, I'm sorry, this is kind of important. Know the decision to make when comparing p-value to significance level. Specifically, if your p-value is less than your significance level, this means you reject the null. So as long as you remember that if your p-value is less than your significance level, you reject the null. Otherwise, you do not reject the null. And there was one more thing, two more things. I know we're over time, but give me 60 seconds, please. If you need to go, I understand. Dang it, left my mind. Oh, know when evidence is significant. And that's when the p-value is less than the significance level. Let me widen this box. Know when evidence is significant. That's when the p-value is less than the significance level. And then the last thing, come on, what was the last thing I was going to say? P-value, significance level. Oh, types of errors, type 1 and type 2. Unfortunately, this was what we did last Wednesday when the Zoom session failed to record. So if somebody keeps on me about it, I'll type up a real quick something summarizing, is this a type 1 error? Is this a type 2 error? Just look at your homework. And in fact, I will post examples of this in Canvas for you to practice for your test. Appreciate you letting me go over time. Sorry about that. See you guys Wednesday. Text me if you have any questions. Zoom crowd, if you got any questions, throw them in the chat. Otherwise, you're good to go. You know, that wasn't that bad for getting such a late start, I guess. I have a class at 10 a.m. tomorrow. I'm free before 10 a.m. You want to do a, well, we can meet. Actually, let me stop recording because we don't need to record anymore. Let me also save this as a PDF. Is it saving? Saved as a PDF. There we go. Okay, let me stop the recording. And let me